Hey everyone, welcome back to Simple Understanding channel. If you're preparing for the APICS Certified in Planning and Inventory Management exam, or planning to begin your journey soon, you're in exactly the right place. This video is part of our CPIM learning playlist, where we simplify complex production and inventory management concepts into clear, practical lessons you can actually apply. Today, we're tackling one of the most important and often most intimidating parts of the CPIM exam, quantitative and operational problem solving. We'll go step by step through 10 realistic CPIM-level math problems, each carefully designed to match the structure, logic, and difficulty of real APICS exam questions. You'll learn how to interpret each scenario, understand what the question is really asking, and think like an operations planner or production manager when solving it. And remember, this video is just one piece of the complete CPIM study materials bundle I've built to help you master every part of the exam, not just the math. Inside the bundle, you'll find summary notes, formula sheets, visual diagrams, practice questions, mock exams, and full step-by-step explanations. Everything you need to understand, apply, and pass with confidence. You'll find the download link for the CPIM bundle in the description below, along with the full playlist, so you can study module by module at your own pace. So, grab your notebook, take your time, and solve along with me. Let's get started. Here are your top 10 CPIM math problems, explained in the clearest and most practical way possible. Problem 1. Forecast accuracy, tracking signal. A planner wants to check whether the company's forecasting method is still reliable. Over the last 6 months, the total difference between actual demand and the forecast added up to 240 units. The average size of those forecast errors, called the mean absolute deviation, is 40 units. Based on this information, should the planner keep using the same forecasting model or adjust it? Problem 1. Forecast accuracy, tracking signal. Data. A planner wants to check whether the company's forecasting method is still reliable. Over the last 6 months, the total forecast error added up to 240 units. The average absolute deviation, or MAD, is 40 units. We need to determine the tracking signal and whether the forecast shows bias. Explanation. Problem 1. Let's check the forecast performance. The tracking signal helps us see if our forecast is consistently too high or too low. To calculate it, we divide the total cumulative forecast error by the mean absolute deviation. When we do that, we find the tracking signal is about +6. That means the forecasts have been consistently higher than the actual demand, a sign of overforecasting. In practice, a value this large tells the planner it's time to review or adjust the forecasting method. Problem 2. Economic order quantity. An item is sold at a steady rate of 9,600 units each year. Every time the company places an order, it costs $50 to process. Holding one unit in stock for an entire year costs about $5. We need to find the order size that minimizes total inventory cost and determine how many orders the company should place each year. Problem 2. Economic order quantity, EOQ. Data. An item has an annual demand of 9,600 units. Each time an order is placed, it costs $50. Holding one unit in inventory for a year costs $5. We need to find the most economical order size and how many orders should be placed each year. Explanation. Problem 2. This one's about finding the most cost-effective order size. The economic order quantity balances two types of costs: the cost of placing orders and the cost of holding inventory. Ordering more frequently increases ordering cost, but reduces storage cost, while ordering in larger batches does the opposite. By finding the balance point, we get the ideal order size that minimizes total cost. In this case, that works out to about 438 units per order, which means the company will place roughly 22 orders per year. At that level, both ordering and holding costs are in balance. The most efficient setup. Problem 3. Reorder point with safety stock. A part is used at an average rate of 80 units per day. It takes about 6 days from placing an order until new stock arrives. During that waiting time, daily demand can fluctuate by as much as 30 units. The company wants to meet customer demand 95% of the time without running out of stock. At what inventory level should the company reorder this item? Problem 3. Reorder point with safety stock. Data. A part is used at an average rate of 80 units per day. The supplier's lead time is 6 days, and demand during that time can vary by about 30 units. The company wants a 95% service level, which corresponds to a safety factor of 1.65. We need to find when to reorder. Explanation. Problem 3. The reorder point tells us the exact moment to place the next order so that new materials arrive before we run out. We start by figuring out how much is used during lead time. 80 units per day for 6 days means the company needs about 480 units just to cover the normal usage while waiting for delivery. Then we add a cushion or safety stock to handle uncertainty in demand. That safety stock adds about 50 extra units. So, the company should reorder when its inventory drops to around 530 units. That keeps service levels high without tying up too much cash in extra stock. Problem 4. Total annual inventory cost. A company sells 12,000 units of a product every year. Placing one order costs $60, and holding one unit in inventory for a full year costs $4. The business currently orders 1,000 units each time. We need to find the company's total annual cost for ordering and carrying inventory. Problem 4. Total annual inventory cost. Data. A company sells 12,000 units of a product each year. Placing one order costs $60, and holding one unit in inventory for a year costs $4. The company currently orders 1,000 units each time. We need to calculate the total annual cost of ordering and carrying inventory. Explanation. Problem 4. Here, we want to find how much the company spends every year on ordering and storing products. First, we find the ordering cost by dividing total demand by the order size. That means the company places about 12 orders a year, each costing $60, a total of $720. Next, we calculate the holding cost. On average, half the order quantity sits in inventory, so 500 units held at $4 per unit equals $2,000 per year. When we add both together, the total annual inventory cost is about $2,720. That number shows the cost trade-off between ordering and holding decisions. Problem 5. Material requirements planning. A finished product requires 2 of component A and 3 of component B. The production plan shows that 400 finished products must be ready in week 5. Component A takes 2 weeks to arrive once ordered, and component B takes 1 week. When should the planner release orders for components A and B so that everything is available when needed? Problem 5. Material requirements planning, MRP. Data. A parent item requires 2 of component A and 3 of component B. The production plan shows that 400 finished items will be needed in week 5. The lead time for component A is 2 weeks, and for component B it's 1 week. We need to determine when to release the planned orders for both components. Explanation. Problem 5. Let's plan when to release the materials for production. We start by multiplying the parent demand by the number of components needed for each item. That means we'll need 800 units of component A and 1,200 units of component B. Now, we look at the lead times. To have everything ready by week 5, we need to order component A 2 weeks earlier, in week 3, and component B 1 week earlier, in week 4. This is the basic logic of material requirements planning, working backward from the parent need date to make sure components arrive just in time. Problem 6, available to promise. The company starts the planning period with 200 units already in stock. In the first week, 300 more units are scheduled to arrive, and confirmed customer orders total 250 units. In the second week, there are no confirmed orders yet, only a sales forecast of 100 units. How many units are available to promise to new customers in the first week? Problem 6, available to promise, ADP. Data. The company starts with 200 units on hand. In week 1, there's a scheduled receipt of 300 units and confirmed customer orders for 250. In week 2, there are no confirmed orders yet, only a forecast for 100 units. We need to find how many units are available to promise to new customers in week 1. Explanation. Problem 6. The available to promise calculation tells us how much inventory we can still commit to new customer orders. We start by adding up the on-hand inventory and the scheduled receipts. That gives us a total of 500 units available in week 1. Then we subtract the confirmed orders, which are 250 units. That leaves 250 units available to promise. Those 250 units can now be safely offered to new customers without risking a stockout. Problem 7. Capacity requirements planning. A work center has 2 machines, and each machine can run for 40 hours per week. Setting up each production batch takes 2 hours, and each unit takes about 12 minutes to produce. 300 units are scheduled for production this week in 3 separate batches. What is the total workload on the work center, and how fully utilized are the machines? Problem 7. Capacity requirements planning, CRP. Data. A work center has 2 machines, each available for 40 hours per week. Each batch requires 2 hours of setup, and each unit takes about 12 minutes to process. 300 units are scheduled for production this week in 3 batches. We need to find the total workload and the utilization rate. Explanation. Problem 7. Capacity planning tells us if our machines can handle the scheduled workload. First, we calculate the setup time. Each of the 3 batches needs 2 hours of setup, which totals 6 hours. Next, we calculate the processing time. Each unit takes about 12 minutes. That's 1/5 of an hour. So 300 units require about 60 hours of runtime. When we add both together, the total load on the work center is about 66 hours. Since 2 machines provide a total of 80 available hours per week, the utilization rate is roughly 82%. That means the work center is busy but still has a little flexibility for extra jobs or maintenance. Problem 8. Yield and scrap factor. A manufacturing process loses about 10% of items due to scrap. If the company needs 900 good units at the end of the process, how many units should it start with to make sure it still meets the target after allowing for scrap? Problem 8. Yield and scrap factor. Data. A process has a scrap rate of 10%. If the goal is to produce 900 good units, we need to know how many should be started at the beginning to reach that target. Explanation. Problem 8. Scrap means some units are lost or rejected during production, so we must start with more than we need. If 10% will be lost, that means only 90% will come out as good parts. To figure out how many to start, we divide the desired good output by the yield rate. When we do that, we find that we need to start about 1,000 units. That way, after 10% scrap, we'll still end up with 900 usable pieces required. Problem 9. Production efficiency. A work center was scheduled to produce 400 standard hours of work this month. In reality, it took 420 hours to complete that same amount of work. What is the efficiency rate of the work center, and what does this result suggest about performance? Problem 9. Production efficiency. Data. A work center is scheduled for 400 standard hours of work this month. In reality, it took 420 actual hours to complete the same amount of production. We need to calculate the efficiency of the work center. Explanation. Problem 9. Efficiency tells us how closely actual performance matches the plan standard. If it takes more hours than expected, efficiency drops. Here, the work center used 420 hours instead of 400, meaning it worked a little slower than standard. When we compare the two, the efficiency comes out to about 95%. That's slightly below the ideal target, suggesting a small opportunity to improve productivity or reduce downtime. Problem 10. Inventory turnover ratio. Over the course of a year, the company's cost of goods sold is $3,600,000. The average amount of inventory it keeps on hand is about $600,000. We need to find how many times the company turns its inventory during the year and approximately how many days of supply that represents. Problem 10. Inventory turnover ratio. Data. The company's cost of goods sold for the year is $3,600,000. The average value of inventory during the year is $600,000. We need to find the inventory turnover ratio and the number of days of supply. Explanation. Problem 10. Inventory turnover shows how many times the company sells and replaces its entire stock during a year. We find it by comparing annual sales cost to average inventory value. In this case, the company turns its inventory about 6 times a year. To express that as days of supply, we divide the number of days in a year by the turnover rate. That gives us about 61 days of supply. This means that, on average, the company holds about 2 months of inventory before it's sold or used in production. And that's it. Those are the top 10 realistic CPM-level math problems, explained step by step. If you found this video helpful, make sure to hit like, subscribe, and turn on the notification bell so you won't miss the next lessons in this CPIM series. Remember, this video is part of the complete CPIM exam preparation playlist, which covers every topic, from master planning and materials management to capacity, scheduling, and performance control. You can find a full playlist link and a download link for all CPIM study materials right below in the description. Thanks for watching Simple Understanding, where we make production and inventory management concepts clear, practical, and exam ready. I'll see you in the next video.